15 gemstones that shouldn't exist, but do. Something is wrong with these gemstones. They break the rules of geology. They contradict physics. Some were forged in volcanic chambers, too unstable to survive. Some were created by meteor impacts violent enough to vaporize continents. And one, the final stone, is older than the earth beneath your feet. These 15 gems should not exist. Their structures are too delicate, their colors too intense, their origins too improbable. They required conditions that happened only once in history or will never happen again. Deep beneath collapsed oceans, inside fossils from vanished creatures, within meteorites that drifted across the solar system, and in deserts where the earth cracked open under impossible heat. These stones formed quietly against all odds. Today they surface as fragments of events the planet cannot recreate. Stones born from accidents, from collisions, from extinction, from silence before the world began. This is a descent into nature's rarest contradictions. 15 gemstones that the earth was never meant to reveal, yet somehow they survived long enough to be seen. Ranked 15th, Larimar, the impossible blue born in darkness. Not every shade of blue is born from water, and not every radiance comes from the sky. Larimar emerges from a place far more turbulent, deeper, hotter, and more improbable than any tropical paradise it resembles. Its story begins beneath an ancient volcanic field in the Caribbean, where the Earth's crust is thin enough to fracture under the slightest shift of tectonic pressure. In this unstable frontier, millions of years ago, columns of silicate-rich magma surged upward through narrow fissures carved into basaltic bedrock. But unlike ordinary volcanic paths, this magma did not erupt onto the surface. Instead, it stalled, trapped in darkness by the weight of the crust above. As it cooled, something rare began to unfold. The temperature, pressure, and alkaline chemistry reached a fragile equilibrium, hot enough to keep minerals in solution, yet cool enough to allow crystals to form without collapsing under thermal stress. In this narrow window, pectolite, a typically dull gray-white mineral, began to take shape. Then came the mistake, a geological misfire so subtle it remains difficult to replicate. Trace amounts of copper and other microscopic ions infiltrated the crystal lattice during its final moments of formation. Their intrusion disrupted the mineral's usual structure, bending wavelengths of light toward an impossible shade, a blue no other pectolite on Earth has ever achieved still. Larimar was far from complete. The Caribbean's violent tectonic uplift had to raise these pectolite veins without crushing them. Groundwater then carved passageways through the volcanic rock, revealing pockets of blue hidden inside. If erosion cut too fast, the veins shattered. Too slow, and they remained entombed in basalt forever. Only one place on Earth struck the balance, a small region in what is now the Dominican Republic here. Magma froze in confinement. Pectolite absorbed the right metals at the right moment. The crust lifted at a gentle pace. The rock weathered at precisely the angle needed for the stone to emerge, and humans arrived late enough to find it before the veins disappeared entirely. A deviation of a single variable, a slightly hotter magma chamber, a marginally stronger uplift, a shift in groundwater flow, would have erased Larimar from geological history, yet it survived. Today, its surface ripples with patterns resembling Caribbean waters at noon. Though it was born nowhere near the sea, its pale whites mimic the foam of distant waves, its deeper blues echo the sky it never touched. Larimar is not an oceanic artifact, nor the reflection of a tropical world above. It is the memory of trapped magma, refined into serenity by forces that should have destroyed it. Larimar remains what it has always been, a trace of volcanic chemistry frozen in a rare moment of equilibrium. No flourish, no miracle, just a brief alignment of heat, pressure, and mineral imbalance that the Earth allowed only once. To study it is not to chase symbolism, but to stand at the edge of a geological coincidence that almost failed to happen at all. Its story ends where it began, in the quiet of a magma chamber that cooled in exactly the wrong, or perhaps the right way. Ranked 14th, UVAROVITE garnet, existing but shouldn't exist because it's too fragile. Among the many forms of garnet scattered across the planet, only one behaves with the discipline of a master craftsman, while its relatives form in clusters, grains, or rough masses. UVAROVITE chooses another path, assembling itself with a mathematical order so exact it feels less like geology and more like intention. Its origins lie inside chromite-rich seams, where chromium saturates the surrounding rock to levels that would disrupt most mineral systems, yet UVAROVITE thrives in this excess. In temperatures rising above 600 degrees Celsius, silicates, oxygen, and chromium begin a measured exchange, bonding with the precision of gears interlocking inside a clockwork engine. The crystal that emerges is neither random nor chaotic. It is systematic, restrained, almost architectural. Most gemstones grow outward in unpredictable directions as they compete for space. UVAROVITE does the opposite. It grows in perfect miniature. Millions of emerald green dodecahedrons, each identical, each aligned in compact arrays across the rock's surface. Their edges meet at angles so consistent that the entire specimen resembles a field of engineered microstructures rather than a natural formation. Under magnification, the geometry becomes even more startling. The facets do not wander. The symmetry does not waver. Each crystal obeys the same internal template: 12 faces, equal angles, consistent termination. A silent discipline guides their formation, as if the mineral understands the boundaries of its own perfection and refuses to exceed them. This precision is further amplified by a color that defies the garnet family's typical palette. While garnets are known for reds, browns, and muted greens, UVAROVITE gleams with an emerald tone so pure it mirrors gemstones far rarer and more prized. The color is not borrowed from inclusions nor enhanced by impurities. It is the direct result of chromium's influence on the crystal's molecular structure, a line-by-line rewrite in the mineral's optical behavior, executed with flawless stability. Such uniformity places UVAROVITE in a rare category within geology. Minerals whose beauty comes not from accident, but from consistency. It does not rely on play of color, fluorescence, or shifting hues. Its appeal lies in the perfection of its form, a natural tessellation laid down over millions of years with unwavering discipline. Yet this precision comes with a constraint. UVAROVITE rarely grows large. Its commitment to structural order limits expansion. The crystals stay small, typically only a few millimeters, refusing the chaotic growth patterns that allow other gem species to form sizable jewels. As a result, UVAROVITE is almost never cut into faceted stones. Instead, it is admired in its purest state, a mosaic of flawless green geometry held together by the rock that hosted it. In geology, perfection is unusual. Nature favors variation, asymmetry, and occasional disorder. But in a handful of deposits across Russia, Finland, India, and Canada, UVAROVITE breaks the pattern. It is nature at its most disciplined, assembling identical forms with a restraint that feels almost engineered. Look closely and the pattern stops abruptly. No grand narrative, no hidden metaphor, just a field of flawless green geometry, ending where the rock runs out. UVAROVITE offers nothing beyond its precision. It does not explain itself. It simply holds the line, crystal after crystal, until there is no more space left to obey the pattern. Rank 13th, Poudretteite, the gemstone that should have broken before it was born. In the hierarchy of minerals, fragility is a sentence to obscurity stones that fracture too easily vanish before they are ever recorded. Yet in a remote corner of the world, a mineral emerged that defies this unwritten law, a crystal so delicate it should have collapsed under the slightest geological pressure. Its name is Poudretteite, a gemstone whose very existence contradicts the principles of mineral survival. The story begins in the Poudretteite family quarry in Mont Saint-Hilaire, Canada, a site known for producing unusual minerals, but nothing as improbable as this pale, bubblegum pink anomaly. The crystal was first identified in the 1960s, not as a gemstone, but as a microscopic specimen measured in millimeters. Scientists logged it with curiosity, then set it aside. A mineral this soft had no path toward reaching the jewelry world. It would break long before it ever grew large enough to matter. For decades, Poudretteite existed only as a laboratory name, a mineralogical footnote, not a gemstone. Its Mohs hardness hovered around a fragile 5. Its cleavage was unpredictable. Its crystal lattice showed weaknesses that should have guaranteed its destruction under the immense forces of tectonic movement. Nothing about it suggested durability. Nothing suggested rarity, and certainly nothing suggested beauty. Then, in an unexpected twist, the impossible happened. In the early 2000s, 3 specimens surfaced from a deposit in Mogok, Myanmar, a region famed for producing rubies and spinels, not geological impossibilities. These crystals were not microscopic. They were not cloudy or fractured. They were large enough to be cut, transparent enough to catch light, and vivid enough to command attention. Their color was a soft, luminous pink that seemed out of place in a mineral species known only from fragile fragments. Geologists were puzzled. How could a mineral so prone to breaking survive the intense metamorphic pressures of Mogok? How could it grow to such sizes without shattering into dust? The Mogok region is a crucible of tectonic violence, a terrain where only the toughest minerals persist. Yet somehow, Poudretteite endured conditions that should have obliterated it. This contradiction thrust the mineral into a new category, a geological survivor that defies its own weakness. The specimens were examined, measured, tested. Their structure revealed no hidden reinforcement, no mysterious stabilizer, no unique impurity strengthening the lattice. Nothing in them made sense. By mineralogical logic, Poudretteite should not exist as a gemstone. It is the equivalent of a glass sculpture surviving a rockslide. Improbable to the point of disbelief, collectors reacted with immediate fascination. Stones like these do not simply appear, they emerge once in a generation. Even among rare gems, Poudretteite occupies a different tier. Not because of its size, not because of brilliance, but because it challenges the expectations of what a gemstone can be. It is fragile but present, soft but luminous, a contradiction that holds its form against overwhelming odds. Today, only a handful of faceted Poudretteite gems exist, most weighing under a carat. Larger specimens belong almost exclusively to museums or private collectors with the means to protect something so delicate. Each stone represents a geological accident, an anomaly preserved long enough for human eyes to witness it, and then, as abruptly as it appears, the anomaly disappears again. No major deposits follow, no stable supply emerges, no assurances remain. Poudretteite surfaces briefly, unexpectedly, and then slips back into geological uncertainty, a mineral that refuses continuity. Its presence is not a promise, it is an interruption. Ranked 12th, Jeremejevite, the crystal whose purity hid in plain sight. For more than a century, Jeremejevite lived in obscurity, a mineral known to specialists, cataloged in journals, but invisible to the world beyond them. It had no spotlight, no mythology, no claim to fame. It was a mineral defined by its absence, too rare for jewelry, too small for museums, too pure to draw attention. Yet hidden within this quiet gem lies a revelation that reshapes our understanding of mineral formation, clarity, and the improbable conditions required to create something so unblemished. Jeremejevite's story begins in the desert expanses of Namibia, where sand dunes shift like oceans of stone, and the ground breaks into pockets of pegmatite, crystallized magma chambers frozen in slow motion. Within these pockets, the mineral grew in near isolation, shielded from the distortions, fractures, and impurities that normally plague crystals. The pegmatite acted as a vault, enclosing the mineral in conditions few stones ever experience: slow cooling, stable pressure, and a chemical environment free from competing elements. For decades, these pockets went unnoticed. When early explorers found Jeremejevite in the late 19th century, they mistook its glass-like transparency for topaz or even quartz. Its clarity was too perfect, too unmarked, too clean. A gem this pure seemed improbable for such a harsh geological environment, a contradiction that delayed its recognition. Only when deeper excavations revealed larger crystals did researchers realize what they were looking at. a mineral that had formed in conditions so stable and uninterrupted that its structure remained almost entirely free from inclusions. Where most gemstones carry birthmarks, gas bubbles, mineral grains, stress fractures, Jeremejevite appeared untouched. A geological life lived without interruption. This revelation rewrote assumptions. Purity was not a luxury of gentle environments, but something that could emerge from extremes, if those extremes aligned in exactly the right sequence. But Jeremejevite held another secret. The mineral is dichroic, meaning it shifts between pale blue, golden, and near colorless tones, depending on the angle of light. This subtle optical shift wasn't just an aesthetic trait, it revealed the delicate imbalances inside its structure, microscopic variations in aluminum and boron content, preserved with astonishing precision. The gem was not a blank canvas, it was a geological record written in light. The more scientists studied it, the more contradictions emerged. How could a crystal so structurally delicate withstand the pressures of deep crustal chemistry without fracturing? How did it remain so chemically pure when pegmatites are often chaotic mixtures of competing minerals? Why did it form in prisms so cleanly defined they resembled laboratory-grown specimens? Each answer revealed another improbability. Jeremejevite is the result of an almost uninterrupted formation cycle. A mineral allowed to grow slowly, privately, without the intrusions or violent shifts that scar most crystals. When larger specimens finally reached the public eye in the early 2000s, collectors reacted with disbelief. The stones looked engineered, as though someone had removed every flaw by hand. They cut cleanly, refracted light with icy sharpness, and showed none of the fatigue expected from natural minerals. For some, it felt like discovering a gemstone from an alternate geological rulebook. After all the clarity and all the misidentification, Jeremejevite's final truth is simple. Nothing dramatic follows. The crystal reveals what it is and then offers no further correction. Its story ends in the plain, unadorned light it always carried. Ranked 11th, Grandidierite, the ocean's legacy trapped in stone. Long before Grandidierite was recognized as one of Earth's rarest blue-green minerals, its story was already woven into the deep memory of the land that birthed it. This gem is not simply a geological curiosity. It is a fragment of a world shaped by ancient oceans, shifting continents, and cultures that read meaning in color long before science defined it. Its origins lie on the island of Madagascar, a landmass that drifted away from the ancient supercontinent Gondwana more than 80 million years ago. That separation sealed the island's identity, creating ecosystems and mineral systems unlike anything else on Earth. Tectonic collisions, volcanic intrusions, and metamorphic transformations turned Madagascar into a geological archive, where each mineral captures a chapter of the island's fractured history. Grandidierite was formed during one of these chapters, a collision event that compressed the crust with such force that sedimentary layers, once part of an ancient seabed, were heated and transformed. Under this pressure, borosilicates reorganized, oxygen bonds restructured, and iron infused the lattice with hints of blue and green. The resulting mineral was rare not because its components were unusual, but because these elements rarely converged in the right order, at the right temperature, and for the right duration. Centuries before its scientific identification, stones with similar hues were sometimes collected along shorelines and riverbeds by coastal communities, prized not for their rarity, but for their resemblance to the shifting colors of water. These early encounters were not documented, but the tradition of reverence for blue-green stones runs deep across maritime cultures. For many, this color represented both boundary and passage, the meeting point of worlds where land gives way to ocean. When French explorer Alfred Grandidierite devoted decades to mapping Madagascar in the 19th century, he recorded the island's geology with meticulous care. Although he never saw the gem that would one day bear his name, his work paved the way for the mineral's classification in 1902. The naming was not merely an honor, it was a recognition that the stone embodied the island's identity, shaped by isolation, complexity, and deep time. Yet Grandidierite remained elusive. Only fragments surfaced for most of the 20th century, often opaque or heavily included. More mineral specimen than gemstone museums held a handful of pieces. Researchers examined them out of curiosity, not expectation. The idea of a transparent, faceted Grandidierite seemed almost mythical. That myth became reality only in the early 2000s, when a small number of transparent crystals emerged from new deposits in southern Madagascar. These stones were not just rare, they were proof of a deeper legacy, that some parts of the earth still held secrets guarded for millions of years. Under light, Grandidierite shifts between teal, emerald, and steel blue, its pleochroism echoing the movement of water across reefs and shorelines. This optical behavior is not merely beautiful, it is a record of the mineral's structural history, a visual expression of the forces that shaped it. Today, faceable Grandidierite remains one of the rarest gemstones on Earth, yet its significance extends beyond rarity or value. It is a relic of Madagascar's geological narrative, one shaped by ancient oceans, continental drift, and the cultural memory of those who have long lived with the rhythms of the sea. Grandidierite's legacy doesn't conclude. It threads into the island that shaped it, no crescendo, no closing flourish, only a color that continues the story Madagascar has been telling for millions of years. Ranked 10th, Sphene, the fire brighter than diamond, held together by fragility. In the world of gemstones, brilliance is a prize earned through strength. Diamonds withstand the Earth's deepest pressures. Corundum resists fracture with near unyielding force. Every luminous stone follows this rule, except when Sphene radiates with a fire greater than diamond, yet breaks under pressure softer than the touch that admires it. It is a gemstone defined by tension, dazzling enough to challenge the greatest jewels, fragile enough to fall apart in pursuit of that brilliance. A paradox shaped in the Earth's crust, pulled between extremes. Its story begins in metamorphic zones, where heat and pressure collide with violent precision. Here, calcium, titanium, and silicate fuse into a crystalline triangle, a molecular structure that should, by logic, produce something sturdy. Instead, Sphene forms with delicate cleavage planes, internal strain, and optical properties so intense they border on instability. Within this structure lies its brilliance and its curse. Light passes through Sphene not as a beam, but as a torrent. Its dispersion, the splitting of light into spectral color, exceeds that of diamond, sending flashes of red, orange, and green erupting from each facet under sunlight. A fine Sphene can appear almost electric, shimmering with spectral fire usually reserved for the most engineered optics. But this radiance comes at a price. The very forces that bend light so dramatically are the same forces that weaken its internal cohesion. Inside the crystal, tension builds even as beauty forms. Geologists studying Sphene often compare it to a bridge under strain, held together by alignment, yet vulnerable to the slightest disruption, a shift in temperature, a change in pressure, an impact measured almost too small to register. Any of these can shatter the stone before it ever reaches the surface. Miners know this tension well. In some deposits, they work with surgical care, brushing away matrix so gently it resembles archaeology more than extraction. A single misangled strike can fracture a crystal worth thousands. In certain regions of Madagascar and Pakistan, miners recount how entire pockets of Sphene turned to powder at the moment of contact, destroyed by vibrations too subtle to detect. Even once freed from the earth, the conflict continues. Lapidaries approach Sphene with a caution reserved for the most brittle materials. They cut not to maximize brilliance, for the stone has more than enough to give, but to avoid awakening internal fractures. Each facet is carved like a negotiation, coaxing fire from the gem without triggering collapse. It is a balancing act between light and loss. Collectors chase the finest examples with a mix of admiration and worry. A flawless Sphene, properly cut, displays such intense dispersion it can appear unreal, as though nature exceeded its own design. Yet those same collectors know the gem's future is uncertain. Wear can dull it, impact can ruin it, time can exploit its hidden weaknesses. Sphene stands alone in the gem kingdom, not because of its brilliance, but because of the tension that defines it, the struggle between what it offers and what it can endure. A gemstone that should have belonged to the ranks of the great, yet was held back by fragility written into its structure from the moment it crystallized. It is beauty under pressure, brilliance balanced on the edge of failure, a stone that should not shine so brightly and should not break so easily, but somehow does both. Ranked 9th, Ammolite, the final light of a vanished ocean. Ammolite is more than a gemstone. It is the final breath of a vanished world, a fossilized record of oceans that once covered North America, sealed beneath millions of years of pressure. But with every fragment that rises into human hands, something ancient disappears forever. Few gemstones embody consequence the way Ammolite does, for its beauty exists only because countless marine lives were extinguished, preserved and transformed beyond recognition. Its origins trace back 70 million years to the late Cretaceous seas that stretched across present-day Alberta. These waters were home to ammonites, coiled cephalopods whose shells shimmered with mother-of-pearl iridescence. They were hunters, drifters, survivors of earlier extinctions. Yet at the end of the Cretaceous, the same cataclysm that ended the age of dinosaurs silenced them as well. Ash clouds, shifting climates, collapsing food chains, all converged to erase their lineage. But in the shallow waters of the Bearpaw Sea, something unique happened. A fraction of these ammonite shells settled into a perfect environment for fossilization. Fine marine mud rich in iron, magnesium, and sulfur. Over millions of years, these sediments compressed, reacting chemically with the shell's aragonite layers. Instead of dissolving, the nacre hardened, locked between mineral films, preserving iridescence in impossible detail. The shells became fossils, and the fossils became ammolite. Its colors are not superficial. They are remnants of biological microstructures, layered like optical records: reds, oranges, greens, blues, each hue formed under different burial pressures. Every fragment is a geological diary of the forces that consumed an ocean. Yet Ammolite does not emerge into the world without consequence. The only commercial deposits lie in a narrow stretch along the St. Mary River, where mining is slow and deliberate. Each extraction removes another piece of a fossil bed that will never regenerate. Paleontologists and miners operate side by side, aware that their work carries weight, uncovering beauty while erasing context. For miners, the consequences are physical. The ground is unstable, the layers brittle. Heavy overburden collapses without warning, and floods from hidden aquifers can erase entire sections in minutes. Ammolite is not a mineral. It is fossilized life, trapped in fragile shale that shatters with a single misjudged strike. Workers describe digging through time with the knowledge that every movement may destroy what they are trying to save. Collectors face a different kind of consequence. Ammolite's surface is so thin that much of it needs stabilization to survive handling. Without careful preservation, colors fade under UV light, and layered aragonite can flake or fracture. To own Ammolite is to inherit responsibility, to protect a remnant of a vanished ocean from the modern world. And there is the deeper consequence: rarity. Only a small percentage of ammonite fossils contain gem-grade Ammolite. Only a fraction of those survive mining intact, and only a small portion of those display the full spectrum that makes Ammolite astonishing. A rolling iridescence that looks less like geology and more like captured fire. Once these deposits are exhausted, no new Ammolite will form. The oceans it came from are gone. The species that created it are extinct. The conditions required to produce its color no longer exist. When the last piece is taken from the ground, the earth will never make another. The colors end where the fossil ends. No rebirth awaits. No geological cycle will return it. Ammolite closes its story with the same finality that shaped it: extinction that has nothing left to give back. Ranked 8th, Rainbow Lattice Sunstone. The geometry that sparked a global obsession. Some gemstones attract admiration, a few inspire desire, but Rainbow Lattice Sunstone does something far more potent. It generates obsession. Not through size, brilliance, or tradition, but through a geometric phenomenon so unlikely that collectors chase it with an intensity normally reserved for relics or astronomical events. The story begins in a remote desert in Australia's Northern Territory, where the land is etched with dry riverbeds and wind-scoured plains. Beneath this desolate surface lies a feldspar deposit that behaved unlike any other known on Earth. As the mineral cooled, microscopic inclusions aligned themselves in precise intersecting angles. Tiny lamellae of hematite and ilmenite arranged with a discipline that seems less geological and more deliberate. The effect is astonishing. When light enters the stone, it doesn't scatter or shimmer. Instead, it unfolds into holographic lattice patterns, crisscrossing rainbows suspended within the crystal, as though some invisible architect etched geometry into sunlight. No other gemstone produces this phenomenon. No other feldspar hosts such perfect intersections of metallic inclusions. Even within the deposit itself, only a small fraction of stones display the full lattice. Parallel bars, intersecting diagonals, iridescent colors shifting along each axis with unnatural precision. This rarity is fuel for obsession. The miners who work the region describe the search as addictive. Days of digging yield nothing but broken feldspar, pale and unremarkable. Then suddenly a fragment catches the sun, a glint, a line, a whisper of geometry, and the hunt begins anew. They return again and again, driven by the possibility that the next strike might reveal a stone carrying the full rainbow lattice, a pattern so crisp it looks engineered rather than formed. Collectors feel the same pull. The first time a rainbow lattice sunstone appeared at a gem show, it was dismissed as artificial, an optical novelty perhaps, or a manipulated specimen. Experts examined it under magnification, expecting to find glue seams, laser interference, or layered composites. Instead, they found nothing artificial at all, just nature behaving in a way mineralogists had never imagined. The discovery ignited a wave of fascination. As word spread, images circulated online. Crystalline grids of shimmering color, floating inside translucent feldspar like coded messages, demand escalated. Collectors from Japan, Europe, and the United States began contacting miners directly, forming networks that traded fragments of information about new pockets, seasonal shifts, production cycles, rumors of exceptional finds. The gem became a global puzzle that people attempted to decode through ownership. For some, the obsession isn't simply about rarity, it's about the feeling that the stone holds a pattern not meant to exist, a geometry usually seen in engineered materials, not the chaotic interior of the earth, a silent logic buried in millions of years of geological noise. But this obsession has consequences. Mining areas are restricted, the land is fragile, and access is tightly controlled to prevent environmental damage. Those who search do so knowing the deposit will not last. The lattice phenomenon requires a sequence of geological conditions that may never repeat: precise cooling, specific chemistry, perfect alignment of metallic inclusions. Once the source is exhausted, the world will not gain another. The search doesn't end with a discovery. It simply pauses until the next glint. Rainbow lattice sunstone never grants closure. It leaves behind the same unfinished chase that defines every collector who looks for it. Ranked 7th. Alexandrite, the two-color gem paid for in danger. Alexandrite is celebrated for its shifting identity. Green in daylight, crimson under lamplight, a stone that seems to carry two worlds inside one crystal. But behind this optical wonder lies a history defined not by color, but by sacrifice. Few gemstones demand so much from the earth, and even fewer exact such a price from the people who search for them. The story begins in the Ural Mountains of Russia, where Alexandrite was first discovered in the 1830s. Not in calm riverbeds or polished alluvial plains, but in some of the most unforgiving terrain miners had ever known. Winters locked the land in months of ice. Summers brought floods that turned pits into churning basins of mud. Tools froze. Tunnels collapsed. The ground swallowed equipment without warning. Yet men returned season after season, drawn by the chance of unearthing a mineral that seemed to violate the rules of color itself. Chromium, the element responsible for the stone's dramatic shift, is rare in the conditions needed to form chrysoberyl. For Alexandrite to exist, chromium must appear in just the right concentration. Too little and the stone remains green. Too much and it darkens into opacity. The earth offers no warnings, no reliable indicators. Miners dig blind, guided only by the hope that one more meter, one more strike of the hammer, may reveal a crystal with the perfect balance of chemistry and clarity. The cost of this pursuit is measured not just in effort, but in loss. Throughout the 19th century, tunnels in the Urals were notorious for cave-ins. Entire shafts collapsed under the weight of snowmelt or shifting bedrock. Many miners who descended into the frozen dark never resurfaced. Their labor remains anonymous, absorbed into the history of a gem that became synonymous with imperial luxury, while those who uncovered it remained invisible. Even for those who survived, Alexandrite demanded sacrifice in quieter, relentless ways. Months away from families, wages that evaporated after equipment costs. The toll of cold and exhaustion carving lines into faces far too young. The gem's rarity amplified its price, but rarely their pay. When the original deposits dwindled, the sacrifice expanded across continents Sri Lanka, Brazil, and Madagascar, revealed new sources, each with its own hazards. In Sri Lanka, miners worked waist-deep in muddy pits that collapsed after monsoon rains. In Brazil, remote jungle deposits required hauling equipment through dense forest, where isolation made accidents nearly fatal. In Madagascar, artisanal miners dug with bare hands, carving shafts through unstable laterite, risking toxic gases and sudden cave-ins for a stone they might never find. The earth gives Alexandrite reluctantly. It demands payment for every piece. And even when a crystal emerges intact, the ordeal continues. Lapidaries must sacrifice much of the rough material to shape the gem. Alexandrite rarely grows clean. Inclusions twist through the crystal like echoes of its violent birth. To reveal the full color shift, the elusive transformation from emerald green to raspberry red, cutters must remove flaw after flaw, surrendering weight to gain brilliance. A gem that begins as several grams may be reduced to a fraction of its size, every lost shard a reminder of the difficulty of its creation. Collectors hold the finished stones as treasures, marveling at the duality of color that seems to defy logic. But the gem's beauty is inseparable from the sacrifices embedded in its history. The minerals consumed, the landscapes carved open, the labor spent, the risks endured. Alexandrite does not offer compensation for what was risked. The tunnels collapse, the mines dry, the stones disperse, and nothing returns the price paid. Its story ends exactly where the effort stopped. Ranked 6th, Opalized dinosaur bone. When ancient life turns into light, there are fossils that tell stories of extinction, and gemstones that speak only of beauty. But opalized dinosaur bone belongs to neither world. It stands at the intersection of life and mineral, a relic transformed by time into something unrecognizable, yet still carrying the memory of a creature that once walked the earth. Every fragment is a reminder that beauty in geology often comes at a cost, and that transformation is never without consequence. Its origin lies more than 150 million years in the past, when massive herds of dinosaurs moved across floodplains that stretched through what is now the American West. These animals lived, fed, fought, and died in landscapes shaped by ancient rivers. When death came, bones were scattered, buried, or washed into sediment. Under ordinary conditions, they would fossilize. Organic matter replaced by silica, iron, or calcite, preserving shape but not color. But in a few extraordinary pockets of the earth, something different occurred. Silica-rich waters seeped through the sediment at precisely the right concentration under temperatures and pressures that shifted slowly over millions of years. Instead of replacing bone with stone in a predictable pattern, these waters carried microscopic spheres of silica that settled into the porous channels of the bone, the same pathways where blood once flowed layer by layer. These spheres formed structures capable of diffracting light. The result was opal, growing inside the architecture of a fossil, transforming anatomy into iridescence. The consequence of this process is profound. A creature that once breathed, moved, and lived is rendered into a gemstone whose colors pulse and shift like trapped fire. What was once bone is now a mosaic of reds, greens, violets, and blues, the spectral residue of an existence reshaped by geology. But this transformation requires conditions so precise they border on impossible. If the sediment is too acidic, the bone dissolves before opal can form. If the groundwater lacks silica, nothing happens. If pressure changes too quickly, the structure collapses. Millions of years must pass with almost no geological disturbance. A single earthquake, a shift in groundwater flow, or a slight chemical imbalance could erase the entire process. Most dinosaur bones experienced these disruptions. Almost none became opal. This rarity gives opalized bone a strange gravity. It is not merely valuable, it carries the consequence of deep time, of lives extinguished, of ecosystems erased. The dinosaurs that left these remains roamed a world that will never return. Their opalized bones are not reminders of abundance, but of finality. Collectors who handle these stones speak of them with a reverence uncommon in the gem world. They do not describe brightness first, or pattern, or fire. They describe weight, the awareness that this shimmer belongs to an animal that lived long before humanity existed. In museums, paleontologists debate how to classify such material, as fossils, gemstones, or something in between. Both answers feel incomplete. Mining introduces another layer of consequence. The deposits lie in fragile terrains. Utah's red deserts, Colorado's badlands. Pockets of Arizona and Nevada extraction risk damaging specimens that took epochs to form. A single careless strike can erase millions of years of history. Many pieces are lost this way, not to erosion, but to human impatience, a reminder that the Earth's slow processes are vulnerable to our fast ones. The opal fire fades into the fossil it inhabits, and the fossil fades into the silence of the ground it came from. No echo of the creature survives beyond this surface. The transformation stops here. Ranked 5th, Paraíba Tourmaline, the neon blue that drove the world to obsession. Paraíba Tourmaline is a gemstone that does not merely attract attention. It alters markets, rewrites priorities, and pulls people into a pursuit from which they rarely emerge unchanged. No other modern gemstone has ignited obsession as fiercely, as suddenly, or as globally. Its neon blue glow, unlike anything produced by nature before, did more than captivate the eye it consumed it. The story begins in the late 1980s when a lone prospector named Heitor Dimas Barbosa drilled through the rugged hills of Paraíba, Brazil. For years, he believed a different kind of tourmaline lay hidden beneath the schist, a belief no one else shared. Workers deserted him. Investors withdrew. But Barbosa persisted, driven not by evidence, but by conviction. He tunneled deeper, pushed further, working in narrow shafts that collapsed as often as they progressed. Local miners called the hill cursed. Geologists dismissed the idea entirely. Then, against all probability, the color appeared. Shards of tourmaline surfaced with an electric, impossible blue, a color so bright it seemed to generate its own light, pulsing like bioluminescence trapped in crystal. It was unlike sapphire, unlike topaz, unlike aquamarine. It was a blue that nature was never expected to make. The discovery hit the gem world like a shockwave. The obsession began immediately. Dealers descended on Paraíba in waves, some arriving with cash in hand, others with armed escorts. Stories spread of buyers offering sums never seen for tourmaline, tens of thousands per carat, later hundreds of thousands for fine pieces. Miners worked through the night by lantern, digging through unstable tunnels in air so thin they fainted at the surface. Even uncut fragments sold before they reached daylight. For many, this was not mining but fever, an immersion in risk fueled by the possibility of uncovering a color that seemed to defy geological logic. The public fed the mania. Jewelers in Tokyo and New York placed orders faster than they could be filled. Collectors competed for stones that vanished into private vaults moments after discovery. Auction houses revised their catalog formats to accommodate a gemstone no one had even heard of a decade earlier. In some circles, Paraíba became a status symbol, not of wealth, but of access, a signal that one belonged to the rare few who touched something that should not exist. But obsession has consequences. Within a few years, the original Brazilian mine was exhausted. The hill Barbosa had sacrificed his life to prove finite. A brief geological accident already stripped bare. When the digging stopped, the world turned scavenger. Dealers hunted for forgotten parcels. Old miners were approached with offers. Even broken crystals were traded at escalating prices, each sale widening the gap between desire and supply. Then came the second wave of obsession. New finds in Nigeria and Mozambique. Their colors approached the Brazilian glow, pushing demand to new extremes. Laboratories confirmed that copper, the same metallic element that made Brazilian stones electric, was present in these gems as well. But purity varied, intensity shifted, and the debates began. Which specimens carried the true color? Which deserved the name? Which were worthy of the mania that started it all? To this day, Paraíba Tourmaline remains a gemstone collectors speak of, not simply with admiration, but with hunger. It is the gem that sparked bidding wars in hotel lobbies, that turned miners into millionaires and millionaires into hunters. A gem whose neon light ignites pursuit with dangerous ease. Paraíba does not merely shine, it summons, it compels, it takes hold. A gemstone that should not glow so brightly, and yet has illuminated the desires of everyone who has ever tried to own it. Ranked fourth, BENITOITE. BENITOITE does not behave like a gemstone formed on Earth. Its optical signature, its crystal geometry, its ultraviolet fire, all of it feels slightly out of place, as though a fragment of some other mineral system drifted into the planet's crust by mistake. Everything about it points toward an anomaly, a stone whose existence contradicts the rules it is supposed to follow. Its journey begins in the mountains of San Benito County, California, a region marked by serpentinite, hydrothermal veins, and tectonic fractures carved by the relentless grinding of the Pacific Plate. These are not conditions known for producing gemstones. They are symptoms of geological unrest, rocks twisted into new shapes, fluids forced through microscopic fissures, temperatures fluctuating too quickly for stable crystals to form. Yet in this chaos, a mineral lattice emerged that should never have achieved clarity or symmetry. BENITOITE crystallizes in triangular formations, perfect sharp-edged stars that no other blue gemstone shares, under visible light. The stone appears a calm sapphire blue, but the anomaly reveals itself the moment ultraviolet light touches its surface. The gemstone ignites, not with a glow but with an electric, ice-blue incandescence, as though it were absorbing darkness and releasing something unearthly in return. The effect does not mimic fluorescence seen in other minerals. BENITOITE's light feels cleaner, colder, and unnervingly intense, the product of trace elements interacting with lattice imperfections in a way no mineralogist predicted. Even the chemistry that formed it is improbable. For BENITOITE to exist, barium must intersect with titanium under hydrothermal conditions that rarely overlap. The required temperatures oscillate between narrow thresholds, too cool and the crystal fails to nucleate, too hot and the structure collapses. The fluids must be rich in silica, yet uncontaminated by competing metals. Pressure must rise and fall in precisely measured pulses. The recipe is so exact that, despite decades of searching, no other region on Earth has produced gem-quality BENITOITE. The stone's anomaly extends beyond formation. In its natural matrix, BENITOITE grows alongside minerals it logically should avoid: neptunite, naturalite, wachanite, each representing chemical environments incompatible with the gem's survival. Geologists studying the deposit describe it as a geological paradox, an assemblage of minerals that should mutually exclude each other, coexisting in a balance held together by conditions so fleeting they likely occurred only once collectors recognized this anomaly instinctively. When the first gem-quality BENITOITE specimens surfaced in the early 20th century, they were mistaken for diamonds. Their brilliance, especially in small crystals, defied expectations for a mineral of moderate hardness. Faceted stones displayed dispersion so high that rainbows fractured across the table with unnatural clarity. Under UV light, the transformation was even more dramatic, an explosion of color where a calm blue gem had been moments before. This dual identity, serene by day, electric by night, fueled an allure that bordered on disbelief. The gem seemed to occupy two states of being, shifting between them with no warning, as though revealing a hidden dimension of itself, only under the right frequency of light. But the greatest anomaly of all is its rarity. The primary mine that produced nearly all fine benitoite is now closed. New material is scarce, often microscopic, frequently included. The world possesses only a finite amount, the remnants of a geological coincidence unlikely to repeat. Benitoite is not simply rare, it is a mistake that endured a mineralogical glitch encoded in crystal. A gemstone shaped by conditions that should not have aligned but did, once, briefly, perfectly. A reminder that even in the strict architecture of geology, the Earth occasionally breaks its own rules. Ranked third. Moldavite. Born in an impact, surviving on a fragile edge. Moldavite begins not as a mineral, but as a moment of violence, a collision that reshaped the sky, burned the earth, and altered the landscape of an entire region. It is a gemstone that carries the tension of two worlds, the cosmic force that created it, and the fragile glass-like body that barely survived the impact. 15 million years ago, a massive asteroid struck what is now southern Germany, releasing more energy than every nuclear weapon on Earth combined. In seconds, bedrock vaporized, forests disintegrated, shock waves rippled across continents. The collision excavated a crater more than 20 kilometers wide, a wound in the Earth large enough to rewrite its geology. But in the center of this devastation, something improbable occurred. The instant the asteroid hit, temperatures soared high enough to liquefy millions of tons of silica-rich sediment. The molten material was hurled skyward, rising through a plume of fire and dust that stretched beyond the atmosphere. For a heartbeat, it hovered between Earth and space, a cloud of incandescent droplets suspended between worlds. Then gravity claimed them. As these droplets fell, they cooled in midair, stretching into aerodynamic shapes, pitted spheres, swirling disks, forms sculpted by speed, heat, and atmospheric friction. Each one carried internal stress, frozen shock, trapped motion, atomic disarray. This was not quiet geological crystallization. It was rapid, panicked solidification, a glass born in flight. When the molten rain reached the Earth again, it shattered across what is now the Czech Republic, embedding itself in sand, soil, and riverbeds. A new mineral had been created, not from magma, not from sediment, but from impact. Moldavite. Its green color comes from iron, its clarity from the violence of its cooling, and its internal etch marks from the atmospheric turbulence that shaped it. Every ridge is the record of velocity. Every bubble is a whisper of the pressure drop as molten rock fell back to Earth. Moldavite's body is tension preserved, a gemstone frozen in the exact moment of its violent birth. But this tension didn't end with its formation. Moldavite is structurally fragile. Its glassy nature makes it susceptible to fractures, chips, and chemical wear. It is a survivor of cosmic force that can be undone by a careless fall. The hardness that allowed it to withstand atmospheric descent contrasts brutally with its vulnerability in human hands, a gemstone born resilient yet destined to remain delicate. This contradiction fuels its cultural tension as well. For centuries, Moldavite was treated with suspicion. Medieval Europeans believed it was a curse, a shard of a star that fell too close to mankind. Others saw it as a relic of the heavens, capable of protecting travelers or revealing truth. In modern times, its rising popularity has split opinion once again. Collectors see it as geological history. Spiritualists treat it as a catalyst for transformation. Scientists view it as a natural record of cosmic violence. And beneath these interpretations lies a deeper tension: scarcity. Only one impact created Moldavite. Only one scatter field exists. Every piece in human possession represents a diminishing resource. As collectors buy specimens and mines run dry, the field's empty. What remains underground grows smaller each year. When the last fragment is lifted from Czech soil, the story ends. There will be no second impact, no renewal, no regeneration. Moldavite carries the tension of creation and extinction at once. A gemstone born from catastrophe, shaped by violence, yet fragile enough to break between two fingers, It is the Earth's reminder that beauty often follows destruction, and that even the most cosmic birth can leave behind something unbearably delicate. Ranked second, red beryl, the desert gem that should not have survived. Red beryl is the kind of gemstone that geology tries to erase, not preserve. Every step of its creation is a contradiction, a sequence so improbable it borders on impossible. Its story begins in Utah's Wah Mountains, a volcanic desert where almost nothing survives, not plants, not water, and certainly not delicate crystals. Yet deep inside these ancient lava domes, the Earth attempted something reckless. It tried to build a gemstone out of the rarest ingredients it had. Beryllium, already so scarce it barely registers in the crust, had to collide with trace manganese at the exact moment volcanic gases were migrating through fractures and cooling rhyolite. The temperature window was razor thin. 1 degree too hot, the crystal dissolves. 1 degree too cold, it never forms. This kind of geological precision isn't rare. It's unheard of. And even when the formula succeeded, red beryl betrayed another contradiction. It grew almost too small to find. Most crystals were thinner than a toothpick. Most broke the moment erosion touched the rock. Millions never reached daylight. Those that did were trapped inside fractures miners describe as harder to detect than a heartbeat in stone. Only a few lived long enough to become gemstones, flashes of saturated red hiding in a desert that should have erased every trace of them. When cutters finally touch the material, the contradictions deepen. The crystals are etched, fragile, and often hollow. More rough is lost than saved. A 1-carat red beryl is a geological miracle. A 2-carat gem borders on myth. And here is the part experts rarely say out loud. There is no second location, no future deposit, no expansion of supply. The conditions that created red beryl only happen once. In one desert, under one set of volcanic events the Earth has never repeated. Every surviving crystal is a leftover from a geological mistake that somehow didn't fail, a gemstone that should not exist, and yet survived long enough to stand at the edge of this list, right before the impossible gemstone that waits in the #1 position. In first place, Hibonite, a stone older than the Earth itself. Before continents formed, before oceans unfolded, before the moon existed, there were fragments of matter drifting through a young and violent solar system, particles forged in temperatures hotter than any volcanic furnace on Earth, carried by winds that came not from air, but from stars collapsing into silence. Hibonite was among them. It is not a gemstone shaped by pressure, time, or the familiar pulse of planetary geology. It is older than all of that. The mineral existed long before the Earth assembled itself from dust and fire. Each grain is a remnant of an era when nothing here had a name and nothing on our planet had yet begun. Hibonite belongs to the calcium-aluminum inclusions, CAIS, the oldest solids ever discovered in the solar system. They formed when the first minerals condensed from the nebular cloud that would one day become the sun and its planets. For a moment, temperatures dropped just enough for matter to freeze. For a moment, chaos paused. Then the silence ended. Shock waves from newborn stars tore through the nebula radiation, stripped electrons from atoms. Gravitational tides twisted the dust into spirals. Most early solids were destroyed, recycled endlessly into the roiling cloud. But a fraction survived, small, unassuming fragments no larger than grains of sand. They endured only because they drifted through pockets of stillness, while the newborn solar system reshaped itself around them. Hibonite was one of these survivors. It is not bright, not showy, not flamboyant. Its beauty is not in color, but in chronology. It does not dazzle, it endures. Within meteorites scattered across Earth today, Hibonite appears as dark crystalline islands sealed inside their ancient hosts. Under magnification, their surfaces show muted reflections, quiet blues, soft bronzes, shadows of structure rather than displays of brilliance. They are not meant to impress. They are meant to persist. And they have. They survived the collapse of the solar nebula. They survived the birth of planets. They survived the era when Earth was molten. They survived 4.5 billion years of collisions, fractures, impacts, wandering through interplanetary darkness. And after all of that, they landed here, on a world that did not exist when they were formed. For scientists who study Hibonite, silence is the first impression. The crystals do not reveal their history easily. Their isotopes speak in half-lives. Their patterns whisper of radiation fields long vanished. They are a record of a time without tectonics, without atmospheres, without life. To hold a piece of Hibonite is to hold an object older than the Earth's crust, older than the oceans, older than the idea of Earth itself. Collectors approach it differently. They do not chase brilliance or symmetry. They chase the pause, the impossible stillness locked inside the mineral. For in Hibonite, nothing is exaggerated, nothing is corrected, nothing is enhanced. It is matter in its first stable form, unpolished by planet building, unaltered by metamorphism, untouched by geological renewal. Every other gemstone on the planet is younger, shaped by cycles of destruction and rebirth. Hibonite alone predates the cycle. It is the absence of Earth, the silence before formation, the quiet before the beginning. To end a journey with such a stone is to acknowledge what the others cannot say, that impossibility is not always spectacular, and that the oldest marvels are sometimes the least adorned. Hibonite is not a gemstone made by the Earth. It is a reminder of the world before Earth, a fragment of the universe's first whisper, surviving long enough for humanity to finally listen. The journey through these 15 impossible gemstones ends here. Stones born from impact, pressure, silence, extinction, and events that may never occur again. Each one is a reminder that the Earth, and everything beyond it, still holds mysteries far greater than what has already been uncovered. If this exploration sparked curiosity or changed the way these materials are seen, a small gesture of support helps these stories continue. A like, a share, or a subscription keeps the door open for the next chapter. But before leaving, one question remains for those who reach the end. Which gemstone challenged your sense of reality the most, and why? The discussion begins there. And the next expedition is already forming, waiting just below the surface.